Welcome to our exploration of waves, a fundamental concept in physics that helps us understand everything from the gentle ripples on a pond to the invisible signals that power our wireless world. In this chapter, we'll dive into the nature of wave motion, the different types of waves, and why they matter. Whether it's sound, light, or even the vibrations in a guitar string, waves are all around us, shaping the way we experience the universe. Let's begin our journey by understanding what exactly a wave is and how it moves energy from one place to another. Wave motion is a fascinating process where energy travels through a medium or even through empty space, without the actual movement of matter over long distances. Imagine dropping a stone into a still pond. The ripples that spread out are waves, carrying energy outward from the point of impact. In wave motion, particles of the medium oscillate around their mean positions, transferring energy from one particle to the next. This is how sound travels through air or how light moves through space. Understanding wave motion is the first step in grasping the broader world of physics. Waves can be broadly classified into two main types: mechanical and electromagnetic. Mechanical waves, like sound or water waves, require a medium, such as air, water, or a solid, to travel through. In contrast, electromagnetic waves, like light or radio waves, do not need any medium and can travel through the vacuum of space. This distinction is crucial because it explains why we can see sunlight from the sun, even though space is a vacuum, but we cannot hear sounds from space. Each type of wave has unique properties and plays different roles in our daily lives. Waves can also be categorized based on how the particles of the medium move. In transverse waves, particles move perpendicular to the direction of the wave's travel. Think of waves on a string or light waves. In longitudinal waves, particles move back and forth in the same direction as the wave, like sound waves in air. This difference affects how energy is transferred and how the waves interact with their surroundings. Recognizing these two types helps us understand a wide range of phenomena, from musical instruments to seismic activity. Fully describe a wave, we need to understand three key terms: wavelength, frequency, and velocity. Wavelength is the distance between two consecutive points in phase, like crest to crest. Frequency is the number of wave cycles passing a point per second, measured in hertz. Velocity is how fast the wave travels through the medium. These properties are interconnected and help us quantify and predict wave behavior in different environments, whether it's sound in air or light in fiber optic. Relationship between velocity, frequency, and wavelength is captured in the simple yet powerful equation V equals F lambda. Here, V stands for velocity, F for frequency, and lambda for wavelength. This equation tells us that the speed of a wave equals its frequency multiplied by its wavelength. It's a fundamental formula in physics, allowing us to calculate any one of these properties if we know the other two. This relationship is key to understanding how waves behave in different media. Principle of superposition is a cornerstone in wave theory. It states that when two or more waves meet at a point, the resulting displacement is simply the sum of the displacements of the individual waves. This principle explains many complex phenomena such as interference and beats, and is essential for understanding how waves interact. Whether it's sound waves overlapping in a concert hall or light waves creating colorful patterns, superposition helps us predict the outcome. Interference occurs when two or more waves overlap and combine to form a new wave pattern. This can lead to constructive interference, where the waves add up to make a bigger wave, or destructive interference, where they cancel each other out. Interference is responsible for many beautiful and practical effects, from the colorful patterns in soap bubbles to the noise-canceling technology in headphones. Understanding interference helps us harness and control waves in technology and nature. Beats are a fascinating phenomenon that occurs when two waves of slightly different frequencies meet. The result is a new sound that seems to rise and fall in volume, creating a pulsing effect. This happens because the waves sometimes reinforce each other and sometimes cancel out, depending on their phase relationship. Musicians often use beats to tune instruments, as the beat frequency helps them match pitches precisely. Beats are a direct result of wave interference in action. Frequency of beats can be calculated using a simple formula. The beat frequency equals the absolute difference between the frequencies of the two combining waves. Mathematically, it's written as F beat equals F1 F2. This means that if two waves have frequencies of 440 Hz and 442 Hz, the beat frequency will be 2 Hz. This formula is widely used in music and acoustics to analyze and tune sounds with precision. Standing waves are a special type of wave pattern that forms when two waves of the same frequency and amplitude travel in opposite directions and interfere. The result is a wave that appears to stand still, with certain points, called nodes, remaining stationary and others, called antinodes, oscillating with maximum amplitude. Standing waves are common in musical instruments where they create the notes we hear. They also appear in many natural and technological systems. Standing waves to form, certain conditions must be met. The medium must allow two waves of the same frequency and amplitude to travel in opposite directions. The boundaries of the medium, such as the ends of a string or a tube, must reflect the waves back. The length of the medium must also be a multiple of half the wavelength. These conditions ensure that the waves interfere in just the right way to create stationary patterns of nodes and antinodes. Fundamental frequency is the lowest frequency at which a system, like a stretched string or air column, naturally vibrates. It's also called the first harmonic. All other frequencies at which the system can vibrate are multiples of this fundamental frequency. The fundamental frequency determines the pitch of the sound produced by musical instruments and is a key concept in acoustics and wave theory. Harmonics are frequencies that are whole number multiples of the fundamental frequency. When a string or air column vibrates, it doesn't just produce the fundamental frequency, it also produces higher frequencies called harmonics. These harmonics add richness and color to the sound, making each instrument's tone unique. The study of harmonics is essential in music, acoustics, and engineering, as it helps us design better instruments and sound systems. Frequency at which a stretched string vibrates depends on its length, tension, and mass per unit length. The formula for the fundamental frequency is F equals 12L times square root T slash mu, where L is the length, T is the tension, and mu is the mass per unit length. This relationship helps us design musical instruments and understand how changing the string's properties affects the sound it produces. Frequency of vibration in an air column, like in a flute or organ pipe, depends on the length of the column and whether its ends are open or closed. For an open pipe, the fundamental frequency is F equals V2L, where V is the speed of sound and L is the length. For a closed pipe, the formula is slightly different. These relationships explain why different instruments produce different notes and how their design influences their sound. Doppler effect is a change in the frequency or wavelength of a wave as observed by someone moving relative to the source of the wave. You've probably noticed this when an ambulance passes by. The siren sounds higher as it approaches and lower as it moves away. This effect is not limited to sound. It also applies to light and other waves. The Doppler effect has important applications in astronomy, radar, and medical imaging. Mathematical expression for the Doppler effect relate the observed frequency to the actual frequency, the speed of sound, and the relative speeds of the source and observer. For sound, the formula is F equals F V plus VO slash V plus Vs, where F is the observed frequency, F is the source frequency, V is the speed of sound, VO is the observer speed, and V is the source's speed. This formula helps us calculate how much the frequency shifts in different scenarios. Doppler effect has a wide range of practical applications. In astronomy, it helps us measure the speed at which stars and galaxies move. In radar technology, it's used to detect the speed of moving vehicles. Medical professionals use Doppler ultrasound to observe blood flow in the body. These applications show how a simple wave phenomenon can have a profound impact on science, technology, and healthcare. Sound intensity is the amount of energy a sound wave carries per unit area per second, measured in watts per square meter. Loudness, on the other hand, is how we perceive the strength of a sound. While intensity is a physical quantity, loudness is subjective and depends on the listener's ear and the frequency of the sound. Understanding the difference helps us design better audio systems and protect our hearing. Waves are everywhere in physics, from the smallest particles to the largest galaxies. Studying waves helps us understand sound, light, earthquakes, and even the structure of the universe. Waves are essential in communication, medicine, engineering, and countless other fields. By mastering the concepts of wave motion, we gain powerful tools to explore and shape the world around us. Waves are not just theoretical concepts, they're visible in the world around us. Ocean waves, ripples in a pond, and even the way leaves rustle in the wind are all examples of wave motion in nature. These natural waves help us understand energy transfer and the interconnectedness of physical systems. Observing waves in nature provides a tangible link between theory and real-world phenomena. Modern technology relies heavily on our understanding of waves. From wireless communication and fiber optics to medical imaging and earthquake detection, wave principles are at the heart of innovation. Engineers and scientists use wave theory to design safer buildings, faster networks, and more accurate diagnostic tools. The study of waves continues to drive progress in many fields. Sound waves are a constant presence in our lives, from conversations and music to alarms and nature sounds. These waves travel through air, water, and solids, allowing us to communicate and experience the world. Understanding sound waves helps us appreciate music, improve acoustics in buildings, and develop technologies like noise-canceling headphones. Light is a form of electromagnetic wave, traveling at incredible speeds and enabling us to see the world. Unlike sound, light doesn't need a medium and can move through the vacuum of space. This property allows sunlight to reach Earth and makes technologies like fiber optics and lasers possible. Understanding light as a wave opens up a world of scientific and technological possibilities. Reflection occurs when a wave encounters a boundary and bounces back into the original medium. This is why we see our image in a mirror or hear an echo in a canyon. Reflection is a key concept in understanding how waves interact with their environment and is used in designing everything from concert halls to radar systems. Refraction is the bending of a wave as it passes from one medium to another with a different speed. This is why a straw looks bent in a glass of water. Refraction is crucial in optics, affecting how lenses focus light and how our eyes see. It also plays a role in sound waves, affecting how we hear in different environments. Diffraction occurs when a wave bends around obstacles or spreads out after passing through a narrow opening. This explains why we can hear someone speaking even if they're around a corner. Diffraction is important in understanding how waves propagate and is used in technologies like loudspeakers and radio transmission. Polarization is a property unique to transverse waves like light, where the vibrations occur in a particular direction. Polarized sunglasses use this principle to reduce glare by blocking certain orientations of light waves. Polarization is also important in photography, LCD screens, and communication technologies. Resonance occurs when a system vibrates at its natural frequency due to an external force matching that frequency. This can lead to large amplitude oscillations, as seen in musical instruments or even in bridges during earthquakes. Resonance is a powerful concept, explaining both beautiful music and destructive vibrations. Waves are efficient carriers of energy. When you pluck a guitar string, the energy travels through the string and into the air as sound. In the ocean, waves transfer energy across vast distances. Understanding how waves transfer energy helps us harness their power in everything from renewable energy to communication systems. Speed of a wave depends on the properties of the medium it travels through. For sound, factors like temperature, density, and elasticity of the medium play a role. For light, the refractive index of the material matters. Knowing these factors helps us control and optimize wave behavior in different applications. A wavefront is an imaginary surface connecting points of equal phase in a wave, like the crest of a water wave. Rays are lines perpendicular to the wavefront, showing the direction of energy flow. These concepts help us visualize and analyze how waves move and interact with obstacles. An echo is a reflected sound wave that arrives at the listener sometime after the direct sound. Reverberation is the persistence of sound due to multiple reflections. Both phenomena are important in designing auditoriums and understanding how sound behaves in different environments. When a wave encounters a material, some of its energy can be absorbed and converted into other forms like heat. This is why heavy curtains reduce noise in a room. Absorption is a key concept in acoustics, insulation, and even in designing stealth technology for aircraft. Transmission occurs when a wave passes through a material or medium. The amount of energy transmitted depends on the properties of the material and the wave. For example, glass transmits light well while concrete does not. Understanding transmission helps us design better windows, lenses, and communication systems. Reflection of waves is crucial in communication systems. Radio and TV signals often bounce off buildings, mountains, or even the atmosphere to reach receivers. Engineers use this property to design networks that ensure reliable signal coverage in cities and remote areas. Seismic waves are waves that travel through the Earth during an earthquake. They help scientists study the Earth's interior and predict the impact of earthquakes. There are different types of seismic waves, including primary P and secondary S waves, each with unique properties and effects. Medical imaging technologies like ultrasound and MRI rely on wave principles. Ultrasound uses high-frequency sound waves to create images of the body, while MRI uses radio waves and magnetic fields. These technologies have revolutionized healthcare, making diagnosis safer and more accurate. Communication systems, from mobile phones to the internet, depend on electromagnetic waves to transmit information. These waves carry signals over long distances, enabling instant communication across the globe. Understanding wave behavior is essential for developing faster and more reliable networks. Music is a beautiful example of wave phenomena in action. The notes we hear are produced by vibrating strings, air columns, or membranes, creating sound waves with specific frequencies and harmonics. Understanding the physics of waves helps musicians tune instruments and composers create harmonious melodies. Many everyday devices use wave principles, from microwave ovens and radios to remote controls and medical scanners. These devices rely on the predictable behavior of waves to function efficiently and safely. Recognizing the role of waves in technology helps us appreciate the science behind our daily lives. Waves are not limited to Earth, they play a crucial role in the universe. Light from distant stars, gravitational waves from colliding black holes, and cosmic microwave background radiation are all examples of waves that help us explore the cosmos. Studying these waves expands our understanding of space and time. The study of waves continues to evolve, with new discoveries and technologies emerging every year. From quantum waves in computing to advanced medical imaging, wave research is at the forefront of innovation. By understanding waves, we unlock new possibilities for science, technology, and society. This chapter, we've explored the fascinating world of waves, from their basic properties and types to their applications in technology, nature, and beyond. Waves are a unifying concept in physics, connecting diverse phenomena and enabling countless innovations. By understanding wave motion, we gain deeper insights into the universe and the tools to shape our future. Keep exploring and let the waves of knowledge carry you forward.